Hi, biology friends. Yes, it is time to take a look at your radiometric dating data and take a look at the lab. A little bit deeper description of what's going on. So you should have this in front of you while you're looking over this video, your M&M-Decay lab, radiometric dating. And that was a link earlier in the week, and you can print that out and follow right along with us. So what are we talking about when we look at radioactive dating? Well, here is the deal. So uranium 236, there we go, is radioactive, and it takes so long for half of uranium, because it's unstable, we talked about this before in the other video, to break down into lead. So this is unstable, and lead is very stable. It's not going to become anything else. So when we date fossils, we say it's 1.2 million years old. This is the technique that scientists use. So everything on the planet has a little bit of uranium in it because it's in the atmosphere. And obviously it doesn't hurt us in small amounts, but rocks have a pretty good amount of it. And what scientists do is they take a look at the amount of uranium compared to lead, and they look at the ratio. So let's say a rock has lots of uranium. It means it is a new rock or young. And if it has lots of lead, it is an old rock, because the less uranium you have, that means the more of it has broken down and become lead. So if you have a little bit of uranium and a lot of lead, you're looking at an old rock. So how do they figure that out? Well, scientists have discovered that it takes so many millions of years for half of the amount of uranium to go away, break down, and become lead. And so this is what we're looking at in this lab, is we're looking at half-lives. All right. So let's scroll down a little bit here. You took a whole bunch of M&Ms and counted them, and they probably should have gotten a half less and half less and half less each time you counted them. And that's what happened in your data, right? So let's take a look at your data here. This is for the girls class. So boys, you have your own data to take a look at. What you have to do for each one of these is you're going to be filling in this table right here with the class total. All right. So let's take a look at your data. If we just go across and we count, not counting mine, because remember, that was just a sample. If we go across from run 1, we count all of these numbers that everybody added, and then we go down and we scroll down and we count the next set of numbers for run 1, all the way across. That's going to be your class. Now, what we actually need is the class average. So you need to do all the work of that math. And let's say you got a certain number, right, for your class total. And then you come back and you enter it onto this graph right here. For run 1, which is what we just counted, let's say, I don't know, we got 800 or something. So I'm going to take my total, 1800, and divide it by the total number of people reporting. So let's say it was 16. And that equals, I added up all your data, by the way, and I got 50.25. I'm writing with my finger. So that's my class average, 50.25. Oh, it's going to kind of fit there. All right. So what am I comparing that to? The probable value, meaning in a perfect world, if you were to shake the bag of M&Ms and pour them out, in a perfect world, half of them would be M side up and half of them would be M side down, right? But your average that you got, 50.25 is really close. 50, there we go. Let's write it really big. It's going to go right there. 50.25, that was really close to the probable value. Now, if you look at the individual data, let's take a look at that for a second here, because that's one of your questions. If we look at the individual data for this, for run one, you had all kinds of numbers. So you had a 60, you had a 48, you had a 42, you had a 54. So individually, you could have been way off. You could have had that 60 number, and that's really not close to 50 at all. But that's not what we did. And that's why we wanted to take a look at your class data. Because if you average all the numbers together, then you get a better value closest to 50, which is half of 100, one half-life. If you take 50 and divide it by 2, divide it in half, you get 25, right? Half of 25 is 12.5, and half of 12.5 is 6.25. So for each one of these over here, each run, that's one half-life. That's one half-life, that's two half-lives, that's three half-lives, that's four half-lives, all the way down. Now, some of you didn't end up going all the way to 10, and that's not a problem at all, right? It's not a big deal. You just entered 0, and then you're going to average that in. So it's not a problem at all. But you see this number over here at the very bottom, 0.098, it's really small. So that's indicating that after 10 half-lives, there's going to be very, very little bit of that uranium. There were very, very, very few of those M side up M&Ms left because you just ran out of them, right? So the M side up represented the uranium or the parent material. The M side down M&Ms represented the daughter material or the lead. So the more lead, the older it is. The less uranium, the older it is. More uranium, the younger it is. The less lead, the younger it is. All right, so let's take a look at graphing your data. You're going to graph both your data and the class average. If you look up here, the directions say to put the data from your group's column on the board. We did that. We kind of did it in that document, right? So on the graph right here, number 8 on the graph, connect your group's data with a black line. All right, so on your sheet, you're going to put all of your data points for you, that's you, your own group, with a black line and connect them. And then you're going to graph the class average with a blue line, right? So you just have two different colors. It doesn't matter if it's black and blue, whatever, just as long as it's two different colors. So let's take a look at what that would look like here. Let's pretend that I'm graphing my data. I'm going to use black. So in one half-life, let's say I got right around 50. So I'm going to do that right there. Boop. So my half-life number 2, let's say I got right around 26. Oops. Then half-life number 3, I got around 12. And then half-life number 4, I got around, I don't know, let's just say 8. Down here. And I'm graphing all of mine. I'm going to connect them with a black line. So that's what it says to do in the directions. Now I'm going to do the class average in blue. See what that looks like. That's going to probably be closer to the 50, right? Closer to the probable. So that's going to be here, blue, and exactly 25. And then exactly, more like 30. Okay, there we go. Down here. My lines are going to be slightly that I used to connect them with. Oops, did not mean to do that at all. Sorry. I'm Sam. I don't want to go back out. That's all right. Stop doing that. So I'm going to end up having two lines. One's going to be black and one's going to be blue. Sorry about that. I was a little, I'm learning this whole thing just like everybody else. So on your graph, you're going to have a black line with your data and a blue line with the class average data. That's what you're graphing on this graph. Then you'd go through and answer the questions. Why didn't each group get the same results? Well, why would you, right? Because it's based on probability and everybody's going to shake the bag a little bit differently. What do the probable values represent? Review in the video because I gave you a big hint on what those represent. Is there anything improbable about the probable values, whether it's applied to M&Ms or to atoms? Is anything ever perfect? Anything ever going to come out exactly like you thought? That's how you're going to answer that one. Which line, the class average or your groups, most resembles the probable values? Take a look. Take a look at your class average data and compare it to probable, and also your data and compare it to the probable. Just tell me how they compare. Do the earlier or later average trials of your class data most resemble the probable values? Probably the later data because they're smaller and it's more difficult to get a difference between those because the difference is so small. Right? So I'm just going to go ahead and give you the answer to that one. It's because the differences are so small down to the last runs there. For how many half-lives do real or simulated atoms behave like probabilistic values? What are the implications for radiocarbon dating and uranium dating? Okay, so radiocarbon dating, I put a video in here for you to help you out with that. What is radiocarbon dating? Carbon's isotope is also another way that we can date things, but with radiocarbon dating, we can only date up to about 2,000 years. Whereas with isotope dating from uranium and plutonium and other things like that, radioactive elements, we can go millions of years because carbon's half-life is shorter. That's why. Because carbon decays much faster and it only sticks around for a certain length of time and then it's just gone. It just breaks down because it's an organic element, right? So take a look at that. If you're struggling with this particular question right here, just do your best job. And I won't even look at that one very much, okay? But this is a good one to look at that video for. Why don't we use radiocarbon dating for dinosaur bones? Think about some of the ages that we've had projected for some of the dinosaur bones we found, like the hominid skulls and hominid skeletons. That's going to be your answer for number 7. Why can't we use radiocarbon? And if you review your video, I told you the answer to that. All right. So if you have any more questions on the lab, just let me know. Hopefully I explained that to you in a way that you understand. I know I'm not there with you, but if you have any more questions, just go ahead and ask them either in Google Classroom or email me and we'll work it out together. So this lab is not due until tonight at midnight. So take your time, do your graph, answer your questions, ask each other. If you have each other's information, but ask me because I probably know the answer. All right. But let me know if you have any questions. Mwah.